Hi Rockridge, this is Mrs. Berger, and this is the day 5 of the Unit 5 on polynomials. Today's lesson is talking about how to graph polynomial functions from the algebra and then also take the graph and make the algebra for the polynomial. So we'll go both ways today. So to graph a polynomial function, you already have quite a few of the tools that you need, quite a lot of the skills that you already need. When you come upon something like question number 1, you'll notice that it is already in intercept form. And so you already know the zeros or roots of the function just looking at the intercepts, the x-intercepts. The end behavior of the function is something we learned with our project. Remember, we looked at the end behavior, we looked at whether the degree was odd or even, and whether the leading coefficient was positive or negative. We also knew from the degree the basic shape of the graph, and we can always find the y-intercept of a graph by setting x equal to 0. So all of that information really builds on skills you already have. The new thing, of course, today is local extrema, so we'll work on that a little bit today as well. So let's start with what we already know. When you look at question number 1, you'll notice that you already have this in intercept form, and so that you know these factors will cause x-intercepts at -2, 0, +3, 0, and -1, 0. Those are the x-intercepts, and I recommend as soon as you know those pieces of information, go ahead and graph them on your grid here so that you don't lose track of what you already know. Let's talk about the y-intercepts as well. Anytime you want to find y-intercepts for any type of function, any kind of polynomial, anything, set x equal to 0 and solve for y. So if 0 is entered here, here, and here, you end up with 2 times -3 times 1. And that, of course, is -6. So the y-intercept is 0, -6, and we'll graph that as well. Now, be careful. That is where this graph crosses the y-axis. It is not necessarily the lowest point of this. Don't be tempted. That isn't the minimum point of this. It's just where it crosses the y-axis. Now, when I looked at this graph originally, I saw that there were 3 factors, and I saw that each of them had a power of 1, or a multiplicity of 1. And when we have this in intercept form, we can count the multiplicities, add them together to determine the polynomial's degree. So the degree of this polynomial is 1 + 1 + 1, which is 3. So this is an odd degree polynomial, and the leading coefficient, the number out in front here, if you were to multiply and distribute all of these factors together into standard form, you would have a positive leading coefficient. And we know that odd degrees with positive leading coefficients act like climbing lines on the ends. Okay? So we know that on this side of the graph, we're ending up going down, and on this side of the graph, we're ending up going up. So I already know that information. I'm going to go ahead and fill that in my table. As x goes to -infinity, this function goes down to -infinity. On the right, as x goes to +infinity, this function on the right goes up to +infinity. Now let's talk about local extrema. Local extrema are just the minimums and maximums in the main portion of the graph. So we're not talking about positive or negative infinity as minimums and maximums. We know those are out there, but as you hone in on little sections of the graph or portions of the graph, what are the highest points they reach and what are the lowest points they reach? We know that this part of the graph here is going to top out somewhere. We just don't know where. And we know this part of the graph will bottom out somewhere. We just don't know where it's going to bottom out. We can ask our calculator to help us find those minimums and maximums. So go ahead, if you need to pause the video, go ahead and enter this into your calculator. I want you to get used to putting these into your calculator. Enter it into y equals. Go ahead and take a look at the graph. And again, if you need to pause to enter this, please do so now. And you'll notice that this is the general shape of this graph. It is certainly a cubic, a degree 3, and it's acting on the ends as we had expected. We just don't know how high that maximum is or how low that minimum is. So here's this maximum. We are going to ask our calculator how high this maximum is. To do that, we will do second, trace. We are asking about a maximum, so that is choice 4. And again, this function is very similar to when we asked the calculator to find the zeros or the x-intercepts. We need to give it a window of locations to look between. So it's asking for a left bound. So it says, how far left do you want me to look? And so I want to go to the left of my maximum. That's good enough. Then I need to set a right bound so that it knows between where and where to look for this maximum. Just make sure you don't include the minimum in this window and you'll be fine. So look between here and here and guess what the maximum is. Yes, go ahead and enter again. Your maximum is located at negative 1.528, comma 1.128. So that is the coordinate of your maximum. So go ahead and pause the video and jot that down in your table. Negative 1.528, comma 1.128. So there's the location of your max, and once you have that information, I highly recommend jotting that onto your graph, sketching it on there. So let's go to approximately negative 1.5 and approximately 1.1. So this graph acts like this, and then it'll come down and cross here. We just need to know how low this minimum is so that we can properly graph that. So let's go to our calculator again and ask where the minimum is. Second, trace. This time we're looking for a minimum, choice 3. And we need to set a left bound and right bound. I'll get a little further away from this max. I don't want it to get confused. This is fine. This is to the left of the minimum. And then I'll scoot over to the right of the minimum. It's down there somewhere, so as soon as I see my cursor, I know it's to the right of the minimum. And then one more enter. When it says guess, I'll hit enter. And this is saying that the minimum can be found at 1.528, comma, negative 13.128. So go ahead and pause the video and jot that down. And once again, I will document this so that I can see it on my graph. That negative 13 is a little further down. So 1.5, negative 13 is approximately here. So notice that that is quite further down than the y-intercept. And I'll go ahead and sketch that in. And don't forget to document this information as well as sketch your graph when you're finished. We don't want all that hard work to go to waste, right? We want to make sure that we include all of that information. So that's what our graph looks like. We used our calculator to help with that. If you are at home without a calculator, you can definitely put this into the Desmos calculator. And if you hover over those maxes and mins, you can get those coordinates. So please pause the video and do that if you need to on desmos.com/calculator. Now, increasing and decreasing intervals. We have the skill set to do this. We just need to make use of the information we just grabbed. So this is an increasing interval. This is a decreasing interval. And this is an increasing interval. And so I'll document these left to right. Increasing, I know I start increasing at negative infinity, and I stop increasing at that little local max, that extrema. The x-coordinate of that is negative 1.528. Then I begin decreasing. At that same location, negative 1.528, I begin decreasing. And I continue decreasing until the minimum coordinate of 1.528. Then I begin increasing. I begin increasing immediately at 1.528 and continue increasing forever to positive infinity. Please don't forget that these are x values. Do not enter y values for these intervals. Only x values to show the regions of the graph that are increasing and decreasing. So let's go ahead and enter the next problem into your calculators. Go ahead and pause the video while you do so. Maybe you can start graphing the intercepts and finding the local extrema before you restart the video. One note I do want to caution you about when you put this into your calculator, make sure that that 1/2 is either put in a fraction form with parentheses around it, or you could certainly type that in as 0.5. If you just type 1/2 into your y equals, the calculator thinks that you are saying 1 divided by, and then all of those factors are on the bottom of a giant fraction, and you don't want that. You just want 1/2 to be your leading coefficient, okay? And so go ahead and grab that, put that into your calculator properly, 1/2 times each of yours, and then make sure that it graphs appropriately. Since we have 4 factors, all with a multiplicity of 1, that means this degree is 4. Your intercepts from an x perspective, of course, are -1, 0, 2, 0, -3, 0, -5, 0. Your y-intercepts are found when you zero out your x's. So you have 1 times -2, that's -2. -2 times 3 is -6. -6 times 5 is -30. -30 times 1/2 is -15. So you have 0, -15 as your y-intercept. Make sure that you get all your x-intercepts in there. Now, like I said, go ahead and pause the video, go ahead and pull your local extrema, and then when you're finished documenting those maxes and mins, check that against this video when you restart. Okay, so hopefully you've had a chance to do that. You documented your first min here at -4.224, -9.530, and so you know this comes down and bottoms out here. And then it comes back up and crosses through this 0 here and tops out at the max of -1.962, 6.010. So it tops out there, and then it comes back down and comes through this 0. It comes through the y-intercept of -15, and then it bottoms out at the other min, which was found at -1.962, 0.935, positive 0.935. -24.064, and then it comes back up and goes through this intercept here. We knew the end behavior was going to be up on the ends. It was an even degree with a positive leading coefficient of +1/2, so we already filled that in. So all we have left to do is to document our increasing and decreasing intervals. Don't forget these are x values only. From the left to the right, we start with -infinity, and we go to -4.224. We begin increasing immediately at -4.224, and we increase all the way up to that max of -1.962. We begin decreasing immediately, 1.962. It continues decreasing until the min of 0.935. And at 0.935, we begin increasing, and we will increase to infinity. Remember, those are x values. Can't say it enough. It's really, really important. If any of that went too fast, please do make sure that you've got either Desmos or your graphing calculator with you as you go through those. You will be expected to do that on quizzes and tests. Make sure that those buttons make sense to you. Let's discuss multiplicity for a bit, and I'm just going to do it on this one problem here. We know that we have x-intercepts of -3 and 1, and we also know that that -3 is a cut through, and we know that that +1 is a bounce of some kind, right? Multiplicities of 2, we learned from our project, are bounces. What we don't know is what kind of bounce. Is it a bounce from the top bouncing off, or is it coming up from the bottom and bouncing off? We can help ourselves understand that without using our calculator by saying, alright, what degree is this polynomial? If we add 1 plus 2, we know that our degree is 3. And we know our leading coefficient is a +2. And so positive odd degrees look like this on the ends. And so we know this thing must look like this on this end, and it must look like this on that end. So we can erase this bottom part. We know this must be acting like that. The only remaining thing that we need to understand is how high up this part goes, because we know this one bottoms out right here at the bounce. And so it would help to know if we knew the y-intercepts. So let's zero this out and zero this out. So we have 2 times 3 times -1 squared. So that's 6. So we know this crosses at 6, 0, 6. And then we know that we've got a min. We've already got the information about our min. It's minimized. Its minimum is found. Its local min is found at 1, 0. We just need to know how high up that max goes. And we'll look at our calculator in a minute for that. As x goes to -infinity on the left, we know that y goes down to -infinity. As x goes to +infinity on the right, y goes up to +infinity. So the last thing we need to find out is from our calculator. Go ahead and pause the video and enter this function as it was originally given to you into the calculator that you have or into Desmos, and we'll check back with you and see how that looks. Alright, so hopefully you found a maximum at -1.667, 18.963, and you documented that for yourself as another extrema. So you have a min and a max. We'll begin, and we'll go ahead and graph that, -1.667, 19 approximately, so somewhere around there. So we really max out quite high up there, and we'll fill in the graph, and then we'll talk about our increasing and decreasing intervals. So we know we're increasing here, we're decreasing here, and we're increasing here. So we begin by increasing from -infinity all the way to that max. Remember, the x-coordinate is used, so -1.667. Then we immediately begin decreasing, -1.667, all the way down to that minimum of 1. And then we immediately begin increasing again from 1 all the way to infinity. Alright, I am actually going to take a break from this concept. You can go ahead and try this and check with your teacher on this. I want to move on to writing polynomial functions when you are given the zeros. So this is a big, gigantic sentence that you might see on a quiz or test. Write a polynomial function of least degree that has rational coefficients, a leading coefficient of 1, and the given zeros. Put your answer in standard form. This is a lot of words to say something that you already know how to do. You know that if you have zeros of -1, 2, and 4, you know that you could write a polynomial of x plus 1, x minus 2, and x minus 4. We learned that with our project as well as several other places. The rest of that wording basically says don't add any other elements with an x that add degrees. Don't add anything to the front of it that would make it a leading coefficient other than this invisible one that's already here. Just work with what you've got from those zeros, but put your answer in standard form. Now, in standard form, that means that you've got, in our case, we've got 3 roots. So ax cubed plus bx squared plus cx plus d. That's what standard form is for this cubic function. So in order to do that, we need to distribute these terms together. It really doesn't matter which ones you start with, just do 2 at a time. I'm going to start with the last 2. So I will leave the x plus 1 alone for now, and I will FOIL together the x minus 2 and x minus 4. So that comes out to be x squared minus 4x minus 2x, so that's minus 6x. And then -2 times -4 is positive 8. At this point, we need to distribute the x plus 1 into the term that we just came up with from FOILing. You can do this one of 2 ways. I do it from side to side, so I'll demonstrate that now, and then I'll erase my work and I will do the box method. Side to side, you distribute each term in the first paragraph, in the first parentheses, into every term of the second parentheses. So I'll first distribute my x to everything. X cubed minus 6x squared plus 8x. And now I'll distribute my 1 to everything. Plus x squared minus 6x plus 8. At this point, I just need to order my terms and collect the like terms. So I have a single x cubed. I have -5x squared, -6x plus 16. Now, if you don't like the side-to-side method, or if you think you're going to get confused or mess some things up, here's another method that you can use. It's called the box method. You'll start with the same 2 parentheses. So let me put those back up there for you. So the box method will take y equals x plus 1, x squared minus 6x plus 8. And we'll set up a box, a 2 by 3 box. And on one side you put your 2 term parentheses, so x and positive 1. And on the 3 side you'll take your 3 term, x squared minus 6x plus 8. And really this is just a way to collect your thoughts. And so in each box you'll have the product of each item on either side. So in this box you'll put x times x squared, making it x cubed. And in this box you'll put x times -6x, so so minus 6x squared. And in this box you'll put positive 8 times x, so that's 8x. And here you'll put 1 times x squared. And here you'll put 1 times negative 6x. And here you'll put 1 times 8. And at this point we just group our terms together, combine like terms. And if you'll notice, that's what we get over here. 1x cubed minus 5x squared. Oh, I must have done my math wrong. See, this is why you do the box method. Negative 6x and 8x should have been positive 2x. And then we had 8. So let me go back and double check this here. X cubed minus 6x squared plus 8x plus x squared minus 6x plus 8. That's where we went wrong. So the box method obviously is a way that you can check your work as well. My apologies to everybody who was following along earlier. So that's the correct answer there. I'm going to do this again, both methods, but there's a little trick to number 6. Number 6, let me clear this for you. Number 6 offers you a -2, a 3, and a 3i as the given zeros. We also need you to know that if ever you have an imaginary root or 0, you also they always travel in pairs, so you also have -3i as well. This also happens with radicals. So if we tell you one of the roots is square root of 2, you should know that there's also a negative square root of 2. If we tell you that there's a root 1 plus I, you should know that there's also a root 1 minus I. Okay? So make sure that whenever you're given a radical as a root or an imaginary root, they always come in pairs, positive and negative pairs. So our first step will be putting this in intercept form. We'll make sure that intercept form is provided in this method, so x plus 2, x minus 3, x minus 3i, and x plus 3i. We'll do the same thing as we did before, except now we have 4 roots, so we know our degree is 4, it's even. And I would recommend grouping the imaginaries together when you FOIL these things together, because nice, pretty cancellation things happen. So when I FOIL the first 2 together, I get x squared minus 3x plus 2x is minus x minus 6. And then when I FOIL the other 2 together, I get x squared. And I'll actually write this out so you can see the canceling. Plus 3ix minus 3ix minus 9i squared. Be careful on that one. These cancel. So now I have y equals x squared minus x minus 6 times x squared. Remember what happens to I squared? That turns into -1. So this is x squared plus 9. So now I've got another 2 by 3. I'll first do it by hand. Hopefully I'll get it right this time. I'll first do it by hand, going side to side, and then I'll do the box method. So notice x squared times x squared is x to the 4th. Be careful with that. Plus 9x squared minus x cubed minus 9x minus 6x squared minus 54. And so when I collect my terms, I get x to the 4th minus x cubed plus 3x squared. Let's see, I've taken care of you, and you, minus 9x minus 54. So hopefully when we do our box method, we'll get the same thing. Let's set up our box. And we will do a 2 by 3 box. It really doesn't matter which side gets the 2 and which side gets the 3, as long as you get everybody in there. So on the side we have x squared and a positive 9. Up top we have an x squared, a negative x, and a negative 6. Make sure that everybody gets their signs come along with them. We distribute. Minus 9x, minus 54, and then we group them. You're by yourself, you are together, you're by yourself, and you're by yourself. So let's check and make sure that everybody came together correctly. Yes, it looks like it matches. So this is your final answer. This is your standard form of the polynomial. I know those are long and it's definitely attention to detail required there. Please make sure that you're pausing the video and going back and checking things if you get stuck anywhere. Now, the last lesson that we will learn today is taking a graph and coming up with the algebra. You have done this several times before, especially on your project, but let's just repeat how to do this. Now, on the key, I think we go all the way down to standard form on each of these. We just saw how long of a process that is, so I'm actually just going to get us to intercept form, and then if you would like the practice of using these to get to standard form, you're more than welcome to check that against the key. When you're looking at the graph, we certainly want to double check and make sure we know where it's intersecting or interacting with the x-axis. So that's the first thing I look for, is the locations, and that's only 2 locations in this graph. So I'm going to document those. If I'm interacting at -3, that must have been caused by a factor of x plus 3. And if I'm interacting at +1, that must have been caused by a factor of x minus 1. Now let's look at multiplicity. This -3 is a cut through, so it must have had a multiplicity of 1. You do not have to write this 1, it's already implied, but just making sure that I've taken care of it. And then this interaction here is a bounce at +1, so this multiplicity must have been 2. Now I double check and make sure that things are looking proper from a leading coefficient standpoint. This is a degree 3 polynomial. 1 plus 2 is 3. I have 2 turns, and so I add 1 to that, I get to my degree 3, so everything's matching up with a degree 3 polynomial. This is acting down on the left and up on the right, just like a climbing line does, and so I know that there must be a +1 leading coefficient on this. You don't have to write that in, it's just making sure that we check for that. Always check for that leading coefficient. So at a minimum on a quiz or test, I would need to see y equals x plus 3, x minus 1 squared. If I ask for standard form, you would need to distribute that out like we did on the last page. Let's look at number 8 and see what's going on from an x-axis perspective. Looks like I've got 1, 2, 3, 4 interactions. So I'll account for those with my intercept form. So it looks like x plus 2 caused this cut through. It looks like x plus 1 caused that cut through. It looks like x plus 0, or just x, caused that one. And it looks like x minus 1 caused that one. I am up on the ends. This is a degree 4 polynomial. 1 plus 1 plus 1 plus 1. They're all cut throughs. I'm up on the ends. It's an even degree. So I have an invisible +1 sitting out front of there. Let's look at the interactions here. We've got an interaction -3, 0, and 2. So I'll account for that with factors of x plus 3, x, and x minus 2. This is a degree 3 polynomial, 1 plus 1 plus 1, so it's an odd degree. The ends don't match. The way that they're not matching is up on the left and down on the right, like a falling line, so that must have had a negative leading coefficient. And for this, I have, it looks like an even degree because it's matching on the ends. I have a cut through, I have a bounce, and I have a cut through. The locations of these, the -1 cut through was caused by an x plus 1 factor. The 0 interaction is caused by just x, and the +2 interaction was caused by an x minus 2. The multiplicity, the exponent on this one is 1. You don't have to write that. The multiplicity of this bounce was caused by a multiplicity of 2. You do have to write that. And this cut through was caused by a multiplicity of 1. 1 plus 2 plus 1 is a degree 4, which is what we were expecting. We were expecting even because the ends are matching down, down. And when they match down, down, we know that there's a negative leading coefficient out front. Alright, so go ahead and attempt your homework. Check with your teacher if you have any questions. Make sure that you understand how to work the calculator for the extreme of the maxes and mins, and let us know if you have questions.